we're moving on to normal distribution as an approximation of Poisson distribution, as well as hypothesis testing. So, guys, hi. Last lesson, we did Poisson as an approximation of binomial. This lesson, we're doing normal as an approximation of Poisson. Okay, so it's quite different from the point of view of how you're approximating. This isn't using Poisson distribution. Okay, this is using normal distribution. Okay, we're going to be using normal distribution today. The hypothesis testing, yeah, we're going to be using Poisson for hypothesis testing, but mainly focused on normal distribution. So if you look at 224, they they love to show the proofs in the textbook, and I love the fact that they show the proof because it's helpful to know where this stuff comes from. But the key thing that I found is if lambda is greater than or equal to 15, you can use normal as an approximation of Poisson. So you can use normal as an approximation of Poisson. What? Wait, what?
So you use if and as
Generally.
Okay.
General rule of thumb, if it's greater than or equal to 15, that's when you can start using. Because as lambda increases, Poisson distribution becomes less skewed. Okay, the lower the lambda, the more skewed it is. But as Poisson starts to get bigger and bigger and bigger, it starts to look more and more normally distributed. So they've given an example on the top of 225 where they've got lambda equals 3 and lambda equals 25. Okay, if you look at lambda equals 3, you've got the positive skewed nature. Whereas if you look at lambda 25, it's looking much more normal. Yeah? Okay, so the cut-off point that we've kind of arbitrarily given is 15. Okay, that means when we are approximating, we're using a normal distribution of lambda lambda. Okay, because your normal distribution is normally mu variance. Okay, but because variance and the mean are equivalent, they're the same value. So it's lambda lambda. Okay, so that's when we are using this. Okay, on 225, they've got an example for us to go over, and I'll speak about this one. So it says the annual number of deaths nationally from a rare disease X can be modelled by Poisson distribution with mean 25. 1 year there are 31 deaths, and it is suggested that the disease is on the increase. What is the probability of 31 or more deaths in a year, assuming the mean has remained at 25? Okay, so all we are doing here is taking our lambda, because it is greater than or equal to 15, and it's 25, so lambda equals 25. We're going to use a normal distribution of 25, 25. Okay. Our normal distribution value for z is x minus x bar over standard deviation. If you remember that, yeah. Cool. You remember z? Yeah. This is where we go. Oh, you need to remember S1. Okay. We're just assuming you know this. Okay. So x minus x bar over sigma. Sigma being standard deviation. Obviously, we've been given variance, so when we use our values here, we're going to use z is equal to our x is 31. That's what we're testing against. However, does anyone know what we have to actually use? Not 31. Can't use 31 here. 30.5. Okay, continuity correction error. Poisson distribution is for discrete data. Normal distribution is for continuous data. So because we're going from discrete to normal, we have to consider inclusivity, exclusivity, and continuity correction error. So if I was to draw a little quick bell curve, we've got mean 25. If there were bars, we'd be looking at the bar 31. But because we're doing greater than or equal to 31, we need to consider the smallest value, which would round to 31, which is 30.5. So we're looking at the group 30.5 and above. We're finding that probability there. Any questions about 30.5? Well, it's all well and good saying no, but maybe someone does have a question. I don't know. Don't know why I've written 50 there, because that should have been 25, but we've got 30.5, got 25. What's our standard deviation? 5, because it's root 25. So I'm just going to use root 25 just because, yeah. Type enter calculator will give us a Z value of 1.1. It might be exactly 1. Yeah, it's exactly 1.1. Okay. And then what do we use to find out the probability? The table. So I gave you a formula sheet the other day. You might not have it. But if you look at your formula sheet at 1.1, you get 0.8643. So oh, you got one already? Cool. Right, so when you look at phi 1.1, it gives you 0.8643. Is that the probability? No. Okay, that's a probability. That's below 30.5. So what do we need to do?
1 minus.
1 minus. So our probability of x being greater than 30.5 would be 1 minus 0.8643, which is 0.1357. Cool? Easy enough? Okay, so key things for normal distribution approximation for Poisson. Lambda needs to be greater than 15, and you just need to remember lambda, mean and variance are equivalent, so that's what you're going to be carrying over into your normal distribution. Okay? Oh, and continuity correction error. Three things, basically. 3 things that you need to be careful with. Right, so that's that. The other thing that I said we're going to quickly look at is hypothesis testing. So we've spent quite a few lessons so far looking at hypothesis testing already, but now we're just going to apply a Poisson distribution to the same concept, okay? Nothing's changed. It's just now we're using Poisson to calculate our probabilities as opposed to binomial, okay? So there's a question on 226, which is about a university and a lightning pole, which gets struck, or a high tower, sorry, that gets struck by lightning approximately 3.2 days per year on average, 3.2 days per year on average. And they're suggesting that due to global warming, there's going to be an increase, and apparently the following year, the tower struck by lightning on 7 days, okay? I'm actually going to change that to 8 days. I'm not going to do the question that they've given. I'm going to change it to 8. So don't pay too much attention to 7 currently. There's a reason I want to change it to 8. Okay, so we're going to change it to 8 days. It says carry out a suitable hypothesis test at 5% significance level and state your conclusion. And then what is the probability of a type 1 error in this test? So 2 questions. Calculate probability. What's the probability of a type 1 error? Okay, so state your null and alternative hypothesis to begin with. So H0 is, they've used mu. Cool. You could probably get away with using lambda. I'm going to use lambda. Lambda is equal to 3.2. It's the same, mean. They both mean mean. Okay. They've stated it in very basic language, saying the population mean mu is unchanged. In reality, it would be better to state that as to what that actually means. So on average, 3.2 strikes per year. Again, I'm using shortened language here just because I'm being lazy. H1, mu is greater than. Okay, we're doing one-tailed. They've suggested an increase only. So we're only looking at one-tailed, so greater than 3.2. On average, more than 3.2 strikes per year. Okay. I should say lightning strikes, but yeah, cool. So we're going to use our assumption that the Poisson distribution is 3.2 to test. Okay, so you always take the belief that nothing has changed as your value. So when we did binomial, we took the probability that they suggested, not the probability that you could probably work out elsewhere. So this is the suggested average. So we're going to use that. They've used a table to calculate it, but I hate the table version. And because we're testing 8, not 7, we're going to test 8, not 7. We're going to do the probability that x is greater than or equal to 8, which is equivalent to 1 minus the probability x is less than or equal to 7. Okay? Is that okay?
Yeah.
Cool. So to calculate that using Poisson, I'm going to use 1 minus e to the minus lambda.
-3.2.
What?
-3.2.
Okay, cool. And then I like the factorized version, so I'm going to use the factorized version. 3.2 to the power 0 over 0 factorial. What's that? Yeah, I've changed it. What of it? I've decided 8 strikes rather than 7. There's a reason. Okay?
No, I was just,
Yeah.
I was just wondering why is it greater than 8?
Why is what greater than or equal to 8? What? No, that's actually a fair question. What? Like, I changed the lightning strikes to 8, so we need to be 8 inclusive for our probability. But then you also need to check all the probabilities beyond that, not just the individual probability of 8 strikes. Because we're talking about a distribution. So if I was to draw the distribution, it would look like that. And what I want to know is 8 or more.
Oh, okay.
How much of a probability was that section? Is that okay?
Yeah.
Cool. 3 factorial plus 3.2 to the power 4 over 4 factorial plus 3.2 to the power 5. Can someone be doing this as I'm writing it down? Because I'm sure you can work out what comes next. I'm running out of space. Don't we just love Poisson and all of the calculations you have to do? Yeah, it's fun. But if you type that into your calculator, you'll end up with a value that roughly resembles 0.0, I'm going to guess.
Oh, why'd you add 8 into it?
What? Because, oh, sorry, shouldn't have had 8, thank you. Good catch. Looks like 2 people are paying attention.
Who's that?
Kabir and I think someone else. Didn't you say?
Yeah.
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 I wasn't listening to you. So, you know. Yeah, oh, cool. All right, did anyone get an answer for that?
Almost.
What?
I ran out of space.
What?
1 minus 0.0168.
0.0168? Okay. So that's a probability. Did it fail the hypothesis test?
Yes.
Yes. Because 0.0168 is less than 5%. Therefore, reject null, accept alternate, hypothesis. It could be, I don't know. Yeah, it is alternative. I knew one was right, one was wrong, and I got the wrong way around. Alternative hypothesis. Lambda is greater than 3.2, more than 3.2 strikes per year. Sorry, on average.
You always accept 1.
If it's under, do you accept null or do you accept alternative?
You accept alternative. Yeah. Because the probability, guys, because the probability is so small of it happening without some form of change, then something must have changed,
Yeah.
is the argument. So because it's below 5%, the probability of this happening is so, unlikely that something must be wrong, is basically the argument. Okay? Right. The reason I included 7 was for that, what is the probability of a type 1 error in this test? Okay. How are you going to find out the probability of a type 1 error? No, this failed the significance test, but what's the first point of a type 1 error? It's where you reject the null without a change. Okay, so we need to find the point at which you would reject the null without a change, which is the the critical value. Okay, so we need to find the critical value in this case. Okay, 8 is not the critical value. Okay, the reason I got rid of a 7 was because 7 is a crit value. So what you'd have actually had to do is find out that crit value 7. It's just they did kill 2 birds with 1 stone, and I didn't like the fact that they didn't properly investigate a type 1 error. That's why I changed it to 8. But what you should have been considering is, at what point is the first time it is below 5%? Okay? And you would have calculated that by doing, again, 1 minus, but you'd have tried up to 6, well, up to 2, 3, 4, 5. So you'd have done that formula several times, starting at like maybe 4, and then gone 4, 5, 6, and added on extra bits each time. And then you'd have ended up with x being equal to 7. And it gives you the probability that x is greater than or equal to 7 as 0.0446. And that is your probability of a type 1 error. Okay? Once you find that crit value, it's the probability of that happening. Okay? Yeah.
When you're trying to find a crit value, it's very challenging, right?
Yeah, it's just inputting into your calculator till you get the right value.
But then you still have to write down every like calculation you did. Or could you just write down the one that's right?
You could just write down one that's right, yeah.
Depends on the marks.
Yeah, it does depend how many marks. I would have at least 2 or 3 iterations of a formula with extra bits added on. But yeah, sorry. So when you find the probability of x is greater than or equal to 7, the probability of that happening is 0.0446. That is your percentage chance of a type 1 error. Okay? Because if it was 6, it will be below that. So it wouldn't be a type 1 error. But as soon as you hit 7 or more, that would create a type 1 error. And you take that probability. Okay? Okay, any questions about that? No. Cool. All right. I think the hypothesis test part was actually harder than the normal part, but maybe you'll disagree. Have a go at those questions, and we are officially done with Poisson distribution.